Hello everyone. My report in the afternoon is the Lutex-based subgrid model for LES. Lutex is not just a vortex identification method. It's not just can show the vortex structures, but the Lutex can also be applied to the dynamic models. So in my presentation, I will introduce the large eddy simulation and the subgrid model, and I will talk about the three Lutex based subgrid scale model from the scalar. Then we extend the model to the vector, so which is non-isotropic and isotropic, and then we dives into the convective Lutex-based SGS model. So in the last model, we discard. We do not use the concept of eddy viscosity. We directly go back to the NS equation and analyze where the error come from and try to find a way to do the correction. So in the study of turbulence is an old and challenging problem, and in terms of the turbulence simulation, so like there are three main methods, right? One is DNS, one is large LES, and one is RANS. DNS just is the method that does not apply any model, do not do any modeling, just use enough grid to directly solve the Navier-Stokes equation, and it resolves all scales of the motion. Its advantages is the result is reliable and accurate, but the problem is its computational cost is very, very high, and it is not practical for complicated problems even today. And LES is the stands for the large eddy simulation. No sound, Oscar. It resolves large scale motion and models the small scale motion. So for the large scale, LES directly solve it, and it adds some SGS models to approximate the effect of the subgrid scale motion. So the computational cost of LES is between the DNS and the RANS, and of course its reliability is also between DNS and the RANS, and the LES can do unsteady, right? So RANS usually is steady, is time average, and the last one is RANS. The last one is RANS. RANS is the Reynolds average Navier-Stokes equation. So its idea is in the engineering, people care more about the time average feature of the flow. So the RANS method solves the time average Navier-Stokes equations, and they model the Reynolds stress. So its advantages is its computational cost is the least, and its reliability is not as good as the two methods previous method. So limitation of RANS is it lack generality. So usually a RANS model can only apply to a certain type of problem. Like there is not a uniform RANS model that can work very well for all types of problems. And in the RANS model, there are many empirical coefficients. Right? The empirical coefficients usually just come from the experiment. And since it only solves the time average equation, we will lose some flow informations. And DNS also has some challenges. The main challenge is high computational cost. It requires the grid. This is an estimate of how many grid it needs to do a DNS cost. So if we do a if we do 3D simulation, so the total number of grid is the Reynolds numbers power of 9/4. So if the Reynolds number is large, the demand for the grid is very high. So it's not affordable for complicated problem. And with the advancement of computing knowledge, the computational cost of LES becomes affordable. So at the very beginning, most people do RANS, right? Because the limitation of computing power. But since we have made great processing computing technologies, so RANS can be affordable and can apply to study some engineering problems. So we, like this presentation, we try to apply Lutex into to build some LES model to see if we can find any good models. To do LES or to build an LES model, so there are four conceptual steps. So one is filtering, right? So in LES we solve large scale motion and model small scale motion. So we do a filtering to filter out the small scale motion. So we do filtering. Then we need to derive the filtered Navier-Stokes equation, just like the RANS, right? RANS is time average Navier-Stokes equation. So we will derive the filtered Navier-Stokes equation, and then we need to model something to close the governing equations. Because of filtering, it will introduce some unknown variables into the equations, and we need some models. Do you include the sound one you shared?
I think we haven't changed it yet. It just said yes, that's good.
Okay. And then the fourth step is just trivial. Like when you finish the first three steps, the first step is just to numerically solve your do the numerical computation. Let's talk about the filtering. So this figure shows you the illustration of the filtering. The thin line is the original signal or the data, and the thick line, the broad line is the like filtered U after filtering. So you can see by filtering the small like small oscillations, right? Small spatial oscillation, or we say the scale motion has been filtered out, and we only leave the main, the motion for the large scale. So you can see from here, and here it filter the fluctuation again. So you can see the filtered fluctuation is not zero, right? So for RANs, the time average of the fluctuation is zero, but here for the LES, the filtered fluctuation, the borderline is not zero, right? It's not zero. And theoretically, the filtering process can be done by the convolution. The convolution. We have a filtering function, and do this convolution, we get the filtered velocity field, and there is a requirement for the filtering function, which is the integral of the filtering function should be 1. And this is the simplest filtering function is the box filter function. So the box filter function is like just take average, right? Take average within in the range, and outside the range it's all zero. So it's just like take average, and it's the simplest filtering function. And the delta is the filter wise. So when we do the filter, we determine how wise or how large is large, right? So we decide what is small. So below the wise delta, so the information filter out. And we also have some other filter functions such as Gaussian, spatial, and Cauchy. And we also can. I also want to introduce the concept of implicit filtering. So we do not need to do the explicit, in fact, because the grid size or the discretization method can act as a filtering. So I show you the picture. So one picture is high resolution and one picture is low resolution. So the pixel in image is analogous to the grid, right, in our computation. So if more pixel is high resolution, low pixel is few pixel is low resolution. So you can see that if it's low resolution, the detail, right? Detail is the subscale motion, right? So it's vague, so it loses some detail. So by the grid itself, it can be act as a filtering. So usually, if you do not have some specific requirement for the filtering, you can just use the grid filtering. That is, don't need to do anything. The grid or the discretizing method itself perform the filtering function. And the filtering operation satisfy some basic relationship. So we have a variable phi, and we filter it. So we have the filtered phi and the fluctuation or the error. And if we filter two variables, it is equal to the filter of each, the sum of two filtered variables. And if we filter a partial derivative, partial t, right? It is equal to the partial, the filtered variable over partial t. Similarly, for the for the spatial partial derivatives, so if we filter the partial phi over partial xi, it is equal to the partial filter the phi over partial filters xi. Unlike ranks, the LES the filter, so the filter filtered is not equal to the filter. So if we filter a variable twice, it's not equal to it filter once. And as can be seen from the previous figure, if you filter the error, the result is not 0. And also we also don't have this identity, and they are not equal. They are not equal. So with this basic relationship in mind, we can start to derive the filtered NS equation. So we consider this incompressible NS equation, and then we filter them. So the continuity equation is easy. Just you filter it, right? Filter the whole things, and it implies the partial this filtered u over partial xj is equal to 0. So in this step, we use this property and this property because it has the addition convention. Right? We use the Einstein summation notation. So the double j becomes the addition. So we also use this property in this derivation. And then we filter the momentum equation. So we just put the filter on both sides, and then use this property. We can separate one filter into the sum of two filters, right? Separate them into three filters. And then we apply this relation. So the filter of the partial derivative becomes the partial derivative of the filter, right? Partial derivative of this filter. And here we also use the condition that it's incompressible. So rho is density. Rho is constant. So it can be viewed as a number. So we have this relation. And if we look at this filtered equation, so we can see this convection term is not the same as the original momentum equation, because it's the filter of the multiplication, and we would like it to be like this, right? So if it can be like this, it just matches the forms of the original momentum equation. So we just add this term both sides and subtract this term to the subtract this term both sides. So we get this filtered momentum equation. So observing this momentum equation, you can see the only difference is this term is the extra term, right? This term, we call this term subgrid scale stress, and this subgrid scale stress comes from the convention term. So this term represents the effect or the influence of the subgrid scale motion, right? In some book they define the tau SGS as this. Some book add a rule, add a density. Some book add a negative sign. So there is not a uniform agreement on what the SGS tau is. So like when you read some content, you need to figure out what his definition from the context. And to close this equation, this subgrid scale stress needs to be modeled. Yes, then we go to the third step, modeling to close the governing equations. SGS, the SGS tau comes from the convection term, right? And we know, like in the momentum equation, we have convection term and diffusion term. So both convection and diffusion can enhance the transport of some physical quantities. So I use the heat transfer as an example. So if we have a bottle of water, if we store it, right, so add more convection, so the heat transfer will increase, right? And if the bottle of water, the fluid has higher diffusion coefficient, right, the heat transfer will be increased. So both convection and the increase the diffusion coefficient can perform the same thing, enhance the heat transport. So in terms of the momentum, so the diffusion coefficient is the viscosity, right? So we increase the viscosity, we can increase the momentum transport. So based on these ideas, we have the eddy viscosity hypothesis, or we can say Booth-Nisk hypothesis. So Booth-Nisk models the SGS stress by using the eddy viscosity. So T represents turbulence, right? So mu T. So the left-hand side term, we know it comes from the convection, right? So the left-hand side is related to convection. So he used the eddy viscosity to approximate the effect of convection. So they have the eddy viscosity, and also we can look at this illustration. So for big eddy is our mesh can resolve. So its effect is already reflected in the convection, right, in our governing equation. But if we have a tiny eddy just inside the cell, so we of course we cannot capture it because it's too small. We cannot resolve it, and what we view is like there's no vortex there, right? Because we do not resolve the vortex, but it does enhance the momentum transportation. So its effect is like having a higher viscosity, right? So that's the eddy viscosity hypothesis. Okay. So we have this eddy viscosity assumption, and we know the constitutive relation between the tau and the this should be Sij. My bad. This should be Sij. There should not be SGS here. So we plug this into this equation, and so here become mu Sij and this is the eddy viscosity assumption, and we do some simplification. So you can see that the effective viscosity is the molecular viscosity plus the eddy viscosity in the eddy viscosity model, and we add another term here. So if we let capital P represent P plus this, you can see the eddy viscosity is just add an additional eddy to the original eddy. But you need to keep in mind that the P you solved is not the original P, it's P plus something. But it will not influence the UVW, so the velocity should be still the same. So and then the question is how to model the mu T, how to model the eddy viscosity. Of course, we have some traditional classical models. The first model is the Smagonsky model. Smagonsky is the scientist who first proposed the idea of large eddy simulation, and he proposed the first model, eddy viscosity model. So it used the rate of strain to model the eddy viscosity. So CS is a coefficient, and delta square. Delta is the grid scale square and times the rate of strain. And Smagonsky model, people have found it has many limitations. So first, it overestimates the eddy viscosity near the boundary, right, or near the or in the laminar region. So people need to use the damping function when people apply the Smagonsky model, or people need to use the dynamic procedure to make the model become more physical. And another well-used model is the wall adapting local eddy viscosity model. The whale model. Whale model is also widely used. It solves the problem that the eddy viscosity is not zero in laminar flow. So the whale model can guarantee theoretically that the eddy viscosity will be zero in the laminar flow. But you can see its expression is so long, so complicated. So it's many, but this is also a widely used model. And then we want to use Lutex into the model. So why is Lutex suitable for modeling the eddy viscosity? So as I previously said, so the eddy viscosity is to compensate or to correct the effect of unresolved eddy, right? So there is an eddy inside the mesh, but we do not resolve it, but it does increase the momentum transfer. So we reflect this effect into the eddy viscosity, and the eddy viscosity should be related to eddy, right? Eddy is another way to say vortex, and the Lutex correctly represents the strength of vortex. So it is very natural that we introduce Lutex into the modeling of the eddy viscosity. And you can look at these two figures. So you can see the three lines in the left figure is similar to the three lines in the right figure. So the left figure is the velocity fluctuation, right? And the right figure is the Liu-Tex 3 components in 3 directions. You can see their form, their pattern are pretty similar, right? So because this high correlation, Liu-Tex is suitable to build a additive viscosity model. And third reason is Liu-Tex automatically gives 0 in laminar flow and at the boundary. So you do not need to worry about the model overestimate the eddy viscosity in laminar region or at the boundary. And this is the expression for the scalar Liu-Tex-based model. This model was first proposed by Ding Yuan and Ding Yuan et al. Yi Qian Wang. Yeah. So they did the pioneer work of introducing Liu-Tex into the LES model. So you can see the model expression is very simple, right? It's a coefficient times the length grid scale squared times the Liu-Tex strength, the filtered Liu-Tex strength. So you can see the eddy viscosity is directly related to the rotation strength. And they did some numerical tests. So first they apply that model into the decaying homogeneous isotropic turbulence. So the left is the energy spectrum of Smargansky model, and the right is the scalar Liu-Tex-based model. These points are the experiment result. So you can see the Smargansky model just has like greatly departures from the experiment result, right? So at this time step it's okay, but at this 2 time step you can see a big difference compared to the experiment result. But look at the Liu-Tex SGS model. The line matched the experiment result very well, right? Very well. Also, the expression is very simple, right? It's just a coefficient grid length squared times the vortex strength, and there are so many vortex identification methods, right? So you may think, okay, if we replace Liu-Tex with Q, would it be good or not? If we replace Liu-Tex with lambda Ci or lambda 2, they are all vortex identification methods. Are they good? They all claim they represent vortex strength. So they perform good. So Dong Xiangrui and I think Yi Qian Wang also is also here. So they did this study. So they replaced not only use Liu-Tex. They have used Q criterion, lambda 2 criterion, Liu-Tex, delta criterion, lambda Ci criterion, and also the Smargansky model. They compare these so many vortex identification methods, and the result is shown in this figure. These points are the experiment result. So you can see Q is very bad, right? Q is very bad. Q criteria is very bad. It's greatly deviates from the experimental result. And the lambda 2 is also not good, right? It's also it has some distance between the experiment. And Lutex, right, this one is Lutex. Lutex is the closest, right? The one that closest matches the experiment best. And this light blue line is the delta. Delta it's not very bad, but worse than the Lutex line, right? And also has lambda CI. Lambda CI is, of course, it's better than the Smagonsky, but not very ideal. And the Smagonsky is not good. So among all these vortex identification methods, who all claim they represent the vortex strength, Lutex is the best one compared with the experiment result. And we look at the result at a different time. So the result I showed before is not an incident, right? So at a different time, we can get similar result. Still, Q very bad, and the lambda 2 better than Q, but also not good. Lutex, okay, still the one closest to the experiment. Delta also slightly worse than Lutex, and the lambda CI better than Smagonsky, but worse than the delta. So under the same framework, and Lutex is the best, right? And this also is also shows Lutex is the best vortex identification method. It represents the vortex strength best among these 5 methods. And they also apply the scalar Lutex-based model to the turbulent channel flow. So they compare the mean velocity profile with DNS, and this line is Smagonsky. Smagonsky, very bad. DNS. DNS is here, right? DNS is here. And if we do not use model, the line is very lower. And the Lutex-based model and the wheel model, their behavior very similar. So the behavior is similar, but if you look at the expression, so Lutex expression is very simple, straightforward, but wheel expression is a long expression. And this is the eddy viscosity. It's normalized eddy viscosity. So 0 and 2 are the boundary, right? 0 and 2 are the boundary. So you can see, of course, Smagonsky is not good. So Smagonsky overestimate the eddy viscosity at the boundary. Right? It's very large. And the behavior of wheel and Lutex are similar. So they become 0 at the boundary. And next, I'm going to show you Lutex is theoretically Lutex must be 0 at the boundary if the boundary is non-slip. First, I show you the pure shear. So if a flow is pure shear, so it means its velocity gradient must be in this format, only has a shear term, and the other entries should be 0, right? So the other entries should be 0. So we just calculate Lutex based on this velocity gradient tensor, and you will get Lutex is 0. And you times the coefficient times the grid scale, you will still get 0. So the eddy viscosity must be 0. The Lutez-based eddy viscosity must be 0. And Will can also achieve this result. So if for this velocity gradient tensor, Will also theoretically 0. If you calculate, plug everything into its expression, you will find it's 0. But for the non-sleeve boundary, for a non-sleeve boundary, suppose the z equal to 0 is the boundary. So uv on the plane is 0 because it's non-sleeve. But we can have partial derivatives along the z direction. So these three elements can be non-zero. Then then if you calculate Lutez from this velocity gradient tensor, you will find Lutez is 0 as well, because it has 3 real eigenvalues, right? 3 real eigenvalues. Lutez is 0. So the corresponding eddy viscosity is 0 as well. But if you apply the same condition to Will model, you will find Will is not necessary to be 0. So like if you plug all these terms into the expression, you will find the S11, S12, S21, S22, S31, S21D, they are all 0. And these 3 terms are non-zero, right? These 3 terms are non-zero. They are 1/2 du, dz, partial u, partial z, partial w, partial z, and S23 is 1/2 partial v, partial z, partial w, partial z. S3d is 2/3 partial w, partial z, partial w, partial z, and we plug these values into the numerator. Into the you can find the final expression is like this: is partial w over partial z parentheses square times something. So from this expression you can see, if partial w partial z is 0, then the Will should be 0. But we don't know. Partial w over partial z is not necessary to be 0. So under this situation, Will eddy viscosity, so it's not necessary to be 0. But we do know the eddy viscosity should be 0 at the boundary, right? At the boundary. So yeah. Okay, and the model I talked about before are all based on the scalar eddy viscosity, right? And the scalar eddy viscosity has some limitations. The first point is an eddy has a direction, so we still look at the convection in the bottle. So if we have a z direction axis, so the convection within the plane, right, in the horizontal plane, should be much stronger than the convection vertical, right? So there may be some vertical convection, but the majority convection is inside the plane. So the convection behavior is not isotropic. So it's using a uniform scalar to reflect the effect of in 3 directions has some limitations, right? It's not very reasonable. And in the model, they usually use a uniform grid scale grid scale. That is the delta square, right? So they use the same delta square for 3 directions. So, and in our CFD, it's very common that we refine the grid in one direction. So the grid shape dimension can be like this. It's a thin, it could be a, so one dimension is very like small and one dimension is very long. And if we consider, of course, the filter wise is different, right? So the filter wise of the vortex in this direction and the filter wise of the vortex in this direction, of course, obviously they should not be the same. But the scalar additive viscosity use a uniform filter wise to like for 3 directions. So this is the second limitation of the scalar additive viscosities. So then we just think about making use of the Lutex vector, right? Lutex vector. We want to making use of these properties. So we extend the scalar additive viscosity into the vector additive viscosity, which is anisotropic. So we still look at this grid. And okay, we can look at this xy plane. So if within this plane there is a vortex, what will this small eddy influence, right? So you can see the small eddy influence the tau yx and the tau xy, right? If there is a rotation inside, it enhance the momentum transfer, right, in this plane, and that is increase the tau yx and tau xy. And what would be the grid filter wise for this vortex? The filter wise is these lines times these lines, right? That's d delta y times delta x. The dimension is still the length squared, right? Delta y also times delta x, the dimension is still length squared. So using that understanding, so the original constitutive relation is tau xy, tau yx is mu times partial u over partial y plus partial v over partial x. So we add additive viscosity. So tau xy and tau yx is influenced by the z direction vortex, right? So we only use the z component of Lutex, and the z direction vortex is rotating in the xy plane. So we only use the delta x and the delta y to act as the future wise. Okay, and the rest are the same. Similarly for tau xz and tau zx. So these two stress is influenced by the y direction vortex. So we put ry, Lutex y here, and the rotation is in the xz plane. So we use the length of x and the length of z. We do the same thing for tau yz and tau zy. So we add the influence of rotation here. So we by doing this, we extend the isotropic scalar additive viscosity to the anisotropic vector additive viscosity, and the choice of the filter wise is more reasonable, right? It's more reasonable, and the rotation strength is also more reasonable. And we use the model to test the flat plate. So this line, the lowest line is the DNS line. This is the U plus Y plus is the mean velocity profile in wall normal unit. So the lowest line is the DNS, and the top line is do not use model but use coarse grid. This grid is each direction we divided by 4. So totally we divided by 64. So this line we use 1/64 of the grids of the DNS. So it's a coarse grid. And if we do not apply any model, the velocity profile is like this. And then if we apply the real model, okay, it's better. It's closer to the DNS line. And if we apply the vector model, well, obvious improvement, right? We get obvious improvement. And this is the skin friction coefficient. So this line is the DNS, and this black line is the vector Lutex subgrid scale model, and these two lines, the purple line is no model, the green line is the real model. So the behavior of no model and the real model are similar. At this region, the vector Lutex model is closer to the DNS skin coefficient, but the transition starts late. So you can see the transition starts late, but it can goes to higher position. But so this part is close to the DNS result. So it has some improvement, and Maria will report this more about this model. I think on the online, right? Online, the third day. Oh, Tuesday. Oh, okay, Tuesday. Sorry, Tuesday. Okay. So even though we extend the scalar eddy viscosity to the vector, to the eddy viscosity, extend the isotropic to the anisotropic. The eddy viscosity hypothesis itself also has some limitation. So first, the SGS stress comes from filtering the convection term. So, but we use diffusion to acknowledge the effect of convection. But we know diffusion is linear, but convection is nonlinear. So this approximation may have some limitations. And yes, the same reason, the eddy viscosity used linear term to approximate nonlinear term. And another issue is viscosity is a physical property of the fluid, right? So we artificially add some virtual viscosity, right? So that may not be very reasonable. And I want to talk more about the linear and the nonlinear. As Dr. Liu showed yesterday, so the non-linear can double the frequency, goes to higher frequency, but the linear cannot. And so the part we modeled is high frequency or low frequency. So this figure shows you the LES actually modeled is the high frequency part, right? So LES is the low frequency we can resolve, but high frequency we model. So the LES model is to model the high frequency part. So the frequency problem cannot be. So the frequency problem cannot be ignored. Okay, then next we just do not use the eddy viscosity hypothesis. So we just go back to the original NS equation and analyze where the error comes from and try to develop some new LES model. So what I do here is I decompose the solution, the velocity into the numerical solution and the error. Okay, numerical solution and the error, and accordingly, the gradient can be decomposed into the numerical solution and the error, and this error is a higher order error compared with the gradient error, because gradient takes derivative, and we know taking derivative reduces the order. So so this is the high order, right? So this error is a high order. For example, if this is the 6th order and we take derivative, it becomes 5th order. So the original one is a higher order error. So we just ignore this and only consider the gradient, the error in the gradient. Then and Dr. Liu has introduced in yesterday that the gradient can be decomposed into three parts: the rotation part, the stretching part, and the shear part. Similarly for its error, so that the error of the rotation part, the error of the stretching part, the error of the shear part, and we know, like for the convection, the rotation, right? The rotation contributes most to the convection. So we just ignore this term and ignore this term, only consider the rotation error from the rotation part. So the accurate, right, or the accurate velocity gradient is the numerical solution plus error from rotation part plus error from the stretching part plus error from the shear part, and then we ignore this term, so it's approximately the numerical solution plus this. This can be viewed as the correction, right? Correction to this. So, and this is the the representation of the rotation part. So it's this. So if we add this correction to the numerical solution, we get a more reliable velocity gradient. And if we write the previous expression in the scalar form, so that means for partial u over partial y, we need subtract something to correct it, right? Subtract the 1/2 RZ error, the error of RZ, right? And then also we for partial u over partial z, we need add 1/2 of the error of the ry, and for partial v over partial x, we need add the 1/2 RZ prime. For partial v over partial z, we subtract 1/2 Rx prime, and partial w partial x, we subtract 1/2 y prime. For partial w over partial y, we plus 1/2 Rx prime, and we do not need to change the diagonal term. They just keep the same. And how do we evaluate the error of Rx, Ry, and Rz prime? Do we model them, right? So in the eddy viscosity, we just model. We know the error is, theoretically, we know the error is subgrid scale stress, and they model it, right? So do we model it? Well, we do not want to introduce any model, so the fewer model, the better. So what we do is we use the resolved to model, not model, to estimate the unresolved, right? So the LES resolves the large scale, and the subscale cannot resolve. In traditional area, they model, but we want to use something to estimate. So what do we use? We use the Liouville similarity. Like if we know the spectrum of Liouville and we know the cutoff wave number, then we know how much is resolved and how much is not resolved. And the resolved is our numerical solution, right? So if we know the ratio of unresolved or over-resolved, and then times our numerical solution, then that would be the estimate of the unresolved term. So that's what they do, and the cutoff number is determined by pi over d, right? D is the distance between two adjacent grid points, and the ratio, right? The ratio of unresolved over resolved is the integration from 0 to the cutoff number, the similarity function, right? This is the resolved. And from the cutoff number to infinity, this is not resolved, right? So we got the ratio. Since it's a vector, so the cutoff number for different plane should be different. So like for the Rx is the YZ plane, right? For the YZ plane, the cutoff number is determined by the delta Y and the delta Z. So this is the cutoff number for Rx, and this is the cutoff number for Ry, and this is the cutoff number for Rz, and the ratio times the filtered, right? That's what we solve from our computation, and the ratio times the resolved is the unresolved, right? The ratio times resolved is the unresolved. Ratio times the resolved is the unresolved. Then we know how to evaluate these unresolved three components of Liouville. Then we see how to modify the original momentum equation. So these are the original momentum equation in x direction, and we change, right? We modify the share, right? Share term. We modify the partial u over partial y. We modify the partial u over partial z, and we do nothing to partial u over partial x. And in the constitutive relation, we have partial u over partial y, partial v over partial x, and these two modifications cancels out each other. So essentially, we don't need to do any modification here. The same thing for the tau zx. So these two corrections cancels out each other, and finally, we do not need to do any modification. So the only modification we do here is modify the convection term, right? It's the convection. We know the error how to say, the error of the LES comes from convection term, and here we directly correct the convection term, and this would be the three momentum equation, right? The corrected momentum equation. So for the y direction, we correct partial v over partial x, we correct partial v over partial z, and for the z direction, we correct partial w over partial x, we correct partial w over partial y. And apart from this, we do not need to do any other correction. Yeah, this proposed model directly modify the convection terms, right? So we do not use the eddy viscosity to acknowledge the effect of convection. We do not use diffusion, right, to approximate convection. And in the derivation of this model, there is no empirical coefficient, right? We don't have any empirical coefficient. The error, the error of Liouville comes from the Liouville spectrum. So we do not have any empirical error, and we do not model anything in the derivation. We do not model anything. We do ignore some high order errors, but we do not introduce any model in here. And also the proposed model is anisotropic, right? And we also apply this model to the flat plate. We compare with the DNS and the whale. We compare with DNS, no model, and whale. So the same thing. The no model, whale, and the convection is 1/64 grids of the DNS. That is each direction divided by 4. Each direction divided by 4. So, and this is the isosurface of Liouville, and we use the same threshold for these 4 figures. So, well, something we can see. So apparently this part should correspond with each other. We all have this structure and this, right? We all have this structure, this structure, and this structure and this, right? This structure and this structure and this. But for the convection model, we have another structure in front of this structure, which is not shown for the no model and the whale. So it's and the interesting is this is later. So the transition position is later. So I cannot say transition position is later because I think the transition starts from here, but it does not have this one. But this one, so here is 400, right? 400, 400, 400. But the structure, the position of this structure is more than later than 400. So and we have one more structure, and I think if we compare with DNS, maybe we have this structure, and also we can look at the ring, right? Look at this ring. So use the same threshold. You can see the wheel here separate, right? Here the first and second ring separate. The no model slightly connects, but our model shows a complete 3 rings. And then this is the velocity profile in wall units. So again, no model, whale, our convection model DNS. there is a obvious improvement, right? So this model closer to the DNS velocity profile. And we also calculated the Reynolds stress. DNS is the blue line. The peak of DNS is around here. So all no model, will, and the proposed model is higher than the DNS. But these three models' behavior are similar. So no model is here. The convection model, the peak is here, and the will model peak is here. So their behavior are very, very close for the U prime. And so in the V prime, so it's not similar. So the blue line is the DNS model, and you can see the peak of will model and the no model is here, right? It's around 4/3 height of the DNS, but our model can reach the same level. So you can see the black. So the will and the no model are here. Like the convection model can goes up to the same height as the DNS model. This is the W prime. DNS is high. No model is low. Will model is better than no model, and our model is better than will. But this improvement is not obvious. It's just slight improvement, slightly close to the DNS. And also we have the U prime, W prime, similar result as the previous one. So DNS is the most bottom, and our is the second bottom, but not sure obvious or a big improvement from no model and will. And this one is the skin fraction. So this is the DNS, and you can see ours, although cannot goes up to the DNS, but it can keeps the high, like the height, right? And the no model and the will, it drops. So in this region, our model is closer to the DNS, but it transits late. But transits late, it should be transits earlier. But slightly late. But I think this region, the model is obvious better than the will and the no model. This model we still has something to do, so it's not finished. So one possible error comes from when we use the spectrum, right? We use the similarity to estimate error, and in that process, the cutoff number. So really it's a plane, right? But we square root it to let it become a one-dimensional. So that part may be not very accurate. So ideally, we need to use the 2D spectrum or something to make it more accurate. So and the summary, so the sub-grayscale stress comes from the convection term, and because the eddy has a rotation, has a direction, so anisotropic LES is more reasonable, and we propose a vector. We extend the scalar eddy viscosity to the eddy viscosity, and also we directly modify the convection term and propose the convective Newton subgrid model. And thank you. Yeah.